All right, let's talk a bit more about angular movement or angular speed. And we want to talk in this video about torque. And torque is basically the angular version of force. It accelerates W, or the angular speed. And in this regards, torque is to W what force is to V. So let's go through those basics again. What I have here is a windmill from TurboSquid. The link is on the right side. And I just give it the texture that it comes with a UV quick shade. And then I split off the wings from the overall windmill. And of course, I scale the whole thing so it makes sense relative to Tommy. Pretty straightforward. So with a split here, I can separate the wings. And what I could use now, of course, to put this into RBD bullet solver is to use an assemble, because it names it and packs it. But the problem with this is we have multiple pieces here. So I would get 63 pieces, which is not what I want. I want the whole thing as one object because I want to rotate it. So instead I can use just a pack, which works great because that means the point is in the center of the wings and will rotate around it. I still need a name attribute though, not necessarily here, but in case I would, I can just use a normal assemble and this will create a name attribute for me because I'm lazy. Of course, a name node would have worked as well. So now what we have is one packed object with a name attribute, and I put this into the RBD bullet solver. So if I press start, what happens, of course, is that the whole thing falls down naturally. So for now, let's just, for this test, turn off under forces the gravity, so that this thing is basically in space and not moving at all. Because what we quickly want to talk about is that I can, of course, set a start velocity, for example, with a point wrangle. And then I said, let's say, just for fun, this thing should move upwards, just to show that this works. There you go. And since there's nothing stopping my wings from flying upwards, this is what's happening. Now I want to rotate that thing with a starting angular velocity, which of course is W. And then I want to rotate in this case around, which you can't see, but this is the Z axis here. So what I would have to do is this, and then you can see it rotates. And if I wanted to change the direction, I just put a negative in here and it rotates the other way around. Okay, straightforward. The thing with both approaches is that V and W are constant speed. So if you look down here, obviously W, or V as before, will not change. But what we also can do is, instead of setting a start velocity, we could, for example, go in and add a constant force to our object. If you would set the force outside, this would work as well, but it would only kind of accelerate your object for a single frame and then it would stop. So it makes more sense to always have accelerations or forces inside of your .NET. And here I use a pop force for now to show how to change the velocity, pretty straightforward. So again, if I want to move this upwards, I can set the force to 0, 1, 0. And the main difference here is if we look into the geometry spreadsheet, and look at V, we can see that the velocity is actually increasing constantly because, of course, force is an accelerating force. But this, of course, changes V. W will still stay the same because force, of course, only changes the translation. So what is the alternative for an angular movement? And that is torque. And we can actually find a pop torque just like we find a pop force. Now let's again try to rotate this thing around Z. So the axis will be 0, 0, 1. And the amount, yeah, let's try 1 and see what happens. Worked well before. But it doesn't seem to do anything. If we look closely, it doesn't seem to move. Well, if we look carefully at the geometry spreadsheet, which is the reason you should always have it open, you can actually see there is something happening. It's just a tiny number, which you can see on the exponent part here. It's just a very, very small number. And then another thing is happening that is a bit weird. It suddenly stops. Let's shorten my frame range here, which for some reason is super long. And let's have a look when the W is stopping. It stops exactly on frame, well, not exactly on frame 48, but it's almost 48. So this should give you an indicator what happened here. Why is it suddenly stopping? This, of course, is the very annoying built-in under advanced bullet solver sleeping time. So let's turn this off first. And then we should have a constant change of W, even though it's tiny, it will never stop. Okay, that's the first problem. Another question is, why is it not really moving much? I mean, okay, sure, let's increase that to 100. And then it still barely moves, but we can see it actually moves. What's going on? Why do we need such high numbers? Well, keep in mind, this is an accelerating force, so technically, by default, it will be stopped by the mass of the object. The thing is, the pop force has this as well, but it has a checkbox saying ignore mass, please. The pop torque, for some reason, doesn't have that, and you can't change it. So keep that in mind. You either have to increase that quite a lot, so let's increase that to 10,000, and you will actually see that this thing is accelerating our angular movement, or you adjust the mass. And we can do this, of course, by default in the solver bullet object. And down here under physical, there is a density, which is, of course, multiplied with the volume of the objects and then creates a certain mass internally. So let's lower this to 10, let's say, and all of a sudden the whole thing will be much faster, as long at least as we reset the simulation. And now you can see it's much faster. So let's lower the number now to something more reasonable, 10 for example, and now, even with a lower number, it works properly. So keep that in mind. The torque, for some reason by default, does take mass into account. So let's increase that to 100 to get a quicker result. And as you can see, just like force does to V, torque does to W, the same, it accelerates the numbers. So what happens here is now that we constantly accelerate our mill wings here, and if we merge that together with our actual building, you can see this starts slow and then goes faster and faster and faster and faster. So this could be interesting if you have something like wind that is supposed to increase the angular movement, and just like force accelerates V, torque accelerates W. Now, one last word before we finish this, because it's pretty straightforward. Instead of using the pop torque, of course, you can also use a pop wrangle, for example, to just set the torque attribute yourself. So, of course, this is a vector, as we've seen. And then you can say, okay, it should rotate around Z and accelerate the rotation around Z with a number of 10. And then you can see with a pop wrangle, this works as well. So you can always set the attribute directly via vex if you want. But again, keep in mind, it will take the mass into account, so you might have to deal with that. So yeah, that's it about torque. Torque is to W what force is to V, and that's about it. So I hope this is helpful. Thanks very much, and see you later. Cheers.